Okay, I'm speaking in English because we have another international presenter here. This year is great that we have so many people coming from other countries here to speak and even to listen presentations at TuxCon. Please applause Edmund. Edmund is well known in the open source communities. He has been on stage at FOSDEM and here's today to talk about Fpga. Edmund?
Thank you very much. To get a little bit of impression who is in the audience, so I want to ask to raise your hand if you know what's an Fpga. The majority. And who already worked with an Fpga? 2, 3. Okay, so more or less. Okay. I'm giving you a talk about Fpga and about the open source tool chain we did. And the first question is always, are you crazy? Why are you doing this? Because the tools are free anyway. I want to talk about the open source tool chain, which is running on this board. So the world unique thing is that the tool chain to program the Fpga does not need a high performance PC. It's running on a Raspberry Pi. The board we did with the Fpga has a memory on it. It's 128K. It's running with 100 megahertz. It has a ton of I/O. It can do VGA. So actually, it's as powerful as the first Apple Macintosh. So I need to quit the demo because by plane it's very difficult and it takes also a lot of time. So I want to go to a little bit of introduction to myself and the team. I'm doing this as a hobby because I have a background as an electronics engineer, but I'm doing my money as a consultant for merchant acquisition, so I'm selling and buying companies. I am mainly the evangelist, the marketing, or the infrastructure guy on the team. Then there's the software genius, which is Clifford Wolf. He reverse engineered the Fpga, he wrote the synthesis tools. Then there is Daniel and Antti. Those are the guys who did all the hardware and the manufacturing, and actually me as the community and funding. So what do we have? This is the complete tool chain. When you know Fpga, you know that you program an Fpga by describing what the digital circuit should do. It's not like a program it's executed. It's like, hey, this is the circuit. If you would want to solder it, you can solder it, but we program it in this chip. You write your behavior of the digital circuit. Then this behavior has to be translated by the synthesis tool into a digital circuit. In Verilog, for example, you define two variables. It's like A and B, and you say, okay, the length of the word is maybe 10 bit, it's 10 lines, and you just say, okay, I want to multiply those two things, and the result is in C. Such a short statement in a Verilog file might result in a digital circuit with 2,000 logic gates. So it's much easier to write Verilog than to actually design the logic gates. Then you have the physical constraints because you want to implement your digital circuit in a chip, and the chip has some limitations. For example, he does have some I/O pins, he has a certain number of digital circuits you can program, and you need to fit your design into the chip. And therefore, the place and route algorithm need to know what type of chip and what constraints the chip has. This program does what on a PCB, on a circuit board, the routing engineer is doing, placing all the chips and drawing, and connecting all the pins. This is doing the Arachne place and route software. This place and route software was written by a guy from the MIT in the last summer. And then the result is a file which describes what function block in the chip will be connected to what other function blocks. So really this result of all this is the description of a digital circuit which does fit in that specific chip. Then we have the program which is IcePack, which is actually programming the FPGA. The IcePack is translating from this description file, which is a textual file, into the binary format. And the binary format then is the configuration file, which is understood by the chip itself. This is the whole tool chain, which is available as open source. So, but there are commercial tools for all the FPGAs from the manufacturers of the chips. The question is then, well, how does the open source tool compare to the commercial tools? Because it's open source and it might be not so good as the commercial ones. So you can see here that the numbers are quite similar, and overall the amount of time to implement a digital circuit is also comparable. So I can say that we are about 20% less efficient than the commercial tools, which is for a tool which was written by volunteers within a year, not that bad compared that the other commercial tools are written since 20 years and millions of dollars have been invested into those place and route and those synthesis tools. If you program an FPGA with a digital circuit, you want to know how fast can I drive that circuit? How fast can I drive it? And there are two ways. The first way is you test it and you drive the frequency higher and higher until it fails. But you never know in what circumstances it would fail. So there is the tool which is the timing analysis, and the timing analysis does tell you how long a circuit needs to switch, and comparing and analyzing how these circuits on the FPGA are connected to each other determine how fast you can write a circuit. And this analysis is required for the place and route, and we have our own timing analysis software. And here you can see that we are very close to the results of the commercial tools. So what you get out of this is that you can trust this tool chain and you can use it as you can use a commercial tool chain. Our tool chain, the software, needs to address real hardware, because just generating a bit stream does not make any sense. You want to use it on real hardware. And we released the tool chain in the summer last year, and the result was that people started to build boards, because it's easier to build boards than to make open source tool chains for FPGAs and reverse engineering the FPGA. So the first device which was supported by our tool chain was the original Lattice ice stick, which cost about $20 US. Something funny happened. As soon as we released our open source tool chain, you could not get any ice sticks any longer because they were sold out for half a year. So it took really Lattice quite some time to figure out how many ice sticks they have to manufacture, because they sold 1 or 2 a month. But as soon as we had our tool chain, everyone wanted to have an ice stick, because at that time it was the only hardware available to try out our tool chain. Then there's the bigger one, the evaluation board, which is not so popular. We did our own board, which differentiates from the other boards that We have SRAM directly soldered on the board. We wanted to demonstrate that a tool chain is also running on the Raspberry Pi, and therefore we made our board ahead. We did a lot of I/O pins so that people can really try out easily different hardware. So we decided to use PMOD connectors, which is a standard, and you can buy a lot of I/O modules like Ethernet, like VGA, PS2, USB, whatever. There are about 120 modules for that form factor. So very easy to try out things. Then about Christmas, there was the NANDland Go board, which is a board for $50 with memory, but also with the small 1K FPGA with 1000 logic gates on it. Then there is the CAT board, which is not yet commercially released, but has an SD-RAM on it. Then there is the Olimex project, which is currently using the 1K FPGA. And I heard yesterday that they will upgrade to the bigger 8K FPGA. And then there is also the Alhambra board. So the ecosystem is spreading with hardware. So choose whatever you want. Boards are available and quite cheap. What do we have on the IP side? IP is a little bit misleading because IP means intellectual property, but we are open source, so there is no property, so it's like blocks, Verilog blocks. This FPGA can be loaded with a 32-bit CPU. It can be loaded with an SPI interface. It can be loaded with an VGA frame buffer. So it can, this FPGA can be anything. For example, here we got a frame buffer driver for LED panel. There is a 32-bit CPU running on it. There's an interrupt controller running on it. There is a memory controller running on it. So that's all within the FPGA. There is a real big community on open source blocks which can be reused for putting it on the FPGA. Here you see the SoC we run on this demo. You got the bus, you got the RAM controller, you got the interface, you got the frame buffer. All this fits into 8,000 logic gates. That's quite an achievement, and if you want to use it, reuse it. So what is the advantage of an open source toolchain? Why care? Because the commercial tools are available for free. You can download them and you can use them, and all projects which you can do on the ICO board or on any ICE project, you could do also with the free tools. But the thing is, learning is very difficult because these packages are huge. They start at 10 gigabyte and you cannot look into it. So for learners, for students, this is not really the way to go. I got called from a professor in the United States, and he said, well, I want to have 10 boards for my university course, but I don't know how many students will show up, so maybe I will need more later. And then he said, well, send me another 30 boards because the course is so popular, and he can hand out the development kit because a student will work and will do his project just on this, a Raspberry Pi, ICO board, and that's the whole thing. And he can demo it, so he doesn't have to carry around a huge PC or a development board. Why open source? Innovation. If you have the source code, you can change it to your own purpose. There was one case this week. A guy posted on the mailing list, I cannot use a parameter as a literal width for the width. Verilog does not support this. That's a limitation of the Verilog language. And Clifford answered, well, I have found out this too, and I implemented 2 years ago. So now the open source implementation is much better than the official Verilog standard. Integration. This guy with Spinel HDL, he is doing his PhD about high-level languages for synthesizing hardware. And he was addressing commercial tools, and he had quite some difficulties to address and to interface with the commercial tools. And I said, well, you know, there's the open source toolchain, try out that. And he integrated his front-end compiler with the Yosis synthesis tool within a day. And he said it was very easy because I could look into it, how it works. Fuse SoC, for example, is an environment where a lot of functional blocks are available, and you just need to select what functional block do you want to have within a system, and this Fuse SoC generates a system on chip just by itself. This is unheard in the commercial world because the most effort in the commercial tools is to integrate functional blocks. Wasteful IP. If you use the commercial tools from Altera or Xilinx, it's very easy to use those functional blocks they have available in their tools. For example, HDMI out, video out. There's a block, you just integrate it into your design and you're done. The problem is, this functional block can do everything. It supports every resolution, it supports every frequency, it supports everything. The problem with that is the resulting circuitry is 10 times larger than it needs to be. But the manufacturer of the tools don't care because they also sell the chip and they want to sell big chips. So they feed you huge functional blocks and don't care. So we did the HDMI block, and our block is really a 10th in size from the official block. But it does support only one resolution and one frequency, but we don't care because we need in the design only one resolution and one frequency. There is a guy in Spain. He is doing a new interface for students and for pupils to learn FPGA programming. And he said, well, I don't want people to write code, I want just drag and drop. And he developed a user interface where you can have these functional blocks, these I/O pins, and have some small code snippets, which this development environment is addressed to students. And he said, well, I integrated with your toolchain, it's very easy. It can be deployed on any Linux machine with 2 commands. So this is really an advantage for open source tools. How is the industry structured? How is it behaving? It's like traditional ones is you design blocks, you have the tools from the commercial tool manufacturer, you have the designer, and you have the chips, and all together is done into a design. It's made to a product like a video camera, and the video camera is then sold. And in reverse, you get the money from the sales through the production, and the production gets paid because of the designing, and the designers pay the programmers and they pay for the chips. But you get the tools for free and you get the IP blocks for free. So the chips need to pay for these tools. This is also the reason why Xilinx and Altera, Xilinx and Altera, Xilinx and Terra. So that's the whole big ecosystem. And they are mainly 80% of the market, these two guys. So the main interest is not to make good tools. The main interest of the industry is to move chips. And for that reason, you have the commercial designers, because those are the ones who move a lot of chips. But there are two other user groups, which is the tinkerers and the learners and the students, and on the other end, the researchers and the startups which try to do something innovative. But those guys don't move chips, and therefore the tools are not made for them. So the tools are made for the people who really work full-time on complex projects, and therefore if you download the tool for free, you are overwhelmed. Students need half a year to just find around their way what to do with these complex tools, because it's not made for them. It's not for students, it's not for part-time programmers, it's for people who make a living out of it, and they're investing their whole career into one tool. So for example, if a programmer is doing Vivado, he will never work with Quartus, because these are different worlds, because those software are so complex to use, so it doesn't make sense to use both softwares. So this is where are tools powerful and tools are complicated. It need to be that way, because that moves chips. And therefore you don't get also tool support for the students. The result that the whole industry is a monopoly or a duopoly with Xilinx and Altera is that there is little innovation. And the little innovation you can see with the language. Verilog was started '84, and just to compare, Python started in '91. So Python is an age-old language, and when programmers, software programmers, come to Verilog, they say, "Wow, what craft? It's terrible language. Why? How can you program that?" The reason is that because usually these designs were made by hardware guys, and they learned the hard way how to do this hardware design. And the thing is, if you have no real flexible tools, there also cannot be any innovation. This is Xilinx and Altera, and you see the commercial tool chain is like you have the compiler, you can write in a high-level language, OpenCL, you generate Verilog code, you generate RTL, you make a place and route, and then you program your FPGA. And the interest of the commercial guys is the bigger, the better. And this is also the reason why they give you free code, because the more free code you use, the bigger the design gets. Here's a table. This is implementing that function, ax squared plus bx. So that's the same functionality. And these guys implement it in different environments. So Maxilla is a programming environment, Vivado is a programming environment, OpenCL programming environment. And the tools are so different that the result are between 71 logic gates and 4,000 logic gates, 5,000 logic gates. They're doing all the same, but they are just very wasteful. And the chip manufacturers don't care. They tell, well, use OpenCL. OpenCL is easy to program. Yeah, but you need 100 times more resources, you need 100 times bigger chips, just because you're not able to program in a really proper programming language for the hardware. FPGA are like green walled gardens. There is the Altera garden, and then there is the Xilinx garden. And as long as you stay within the garden, the vendor is happy. And the programmer is happy, but who is not happy is the boss of the programmer, because he needs to buy a chip which is 100 times bigger. And it's very difficult to port different functional blocks between these two ecosystems. So, but that's good for the company because it's lock-in. And lock-in means you can make a lot of money. We had that already in the 90s with the Unix wars. if one stack, if you have this big stack and one part is propriety, then the rest of the stack cannot move forward. So the whole stack needs to be open source. It's not useful if you have only the editor, which is open source, and the compiler, but the place and route is propriety. Because this proprietary tool is holding back the whole tool chain to move forward, to be innovative. Because I am doing this because I expect that there will be new programming languages, new programming tools that really unchain the functional power of FPGAs. So that's the whole stack, and innovation comes from the use case and need to be implemented on the application, in the development environment, in the whole stack. So innovation is not just here, innovation needs to be in the whole stack. As we heard in the last speech, you can speed up any application if you understand the whole stack and not just the Java layer. What we are doing with our toolchain is that Yosis can also feed place and route software from Xilinx and the place and route tool from Altera, but this would hinder the innovation speed, so therefore we really try to have the full stack ourselves. When should you use FPGA? And I advise you to think hard when to use it. Try everything else. If it can be done in a microcontroller, it's much easier to do in a microcontroller. If it can be done in JavaScript, do it in JavaScript. FPGA is really hard, but it's very powerful. And things can be done in FPGAs which cannot be done in anything else. What are the criteria, or what is a typical project which requires an FPGA? If you have a lot of bandwidth, like let's say you want to do a logic analyzer which is pushing a lot of data very fast, this cannot be done with a microcontroller. If you need low latency, it's like you want to measure distance with radio frequency and you have a really fast running counter, you cannot do this with a CPU because you have interrupts in there. So low latency demands FPGA. Precise timing. That's CERN in Switzerland is using a lot of FPGAs because they need to synchronize all their hundreds, thousands of sensors on a precise time step because they need to know what event happened when. And they're using FPGA because of the precise timing. If you want a machine which you can rely on, like an airplane, which should not reboot during flight, then an FPGA is a good solution. Because with an FPGA you can formally prove that it will run always and it will not crash. It's difficult, but it's possible. So you can formally prove, which with software you cannot. You cannot prove with software that it will not crash. With an FPGA you can do that. And, well, application which has a strong logic requirement. This is strange logic requirement when it's really difficult to implement because so many things happen in parallel and you can really just not implement it in sequential programming, then FPGA is the way to go. Some examples for that. We all think in 8-bit, 16-bit, 32-bit, but it turned out that 5-bit is very good too, because a multiplier 5 by 5 needs much less resources than a multiplier 8 by 8. A 8 by 8 multiplier might be 20 times larger than a 5 by 5 multiplier. But the thing is, with neural networks, you don't need 8-bit. So Google implemented a chip specific with 5-bit multipliers because they are much smaller, and for the neural nets it doesn't make any difference. 5-bit is sufficient for them. Smart sensors. More and more logic goes in the front of the system, and if you want to integrate sensors which have precise timing, which are time-dependent sensors, which if you want to do sensor fusion, FPGA is a very good thing. New memory compute architecture. Well, we live in von Neumann times, but von Neumann is very old, and maybe you are a very creative person and you have a new architecture in your mind. The only way to do is to simulate it, which is very slow, or you implement it in an FPGA. The FPGA is running 100,000 times faster than the simulation on your PC. Interval math, different number formats, unum, whatever, your crazy idea. The thing is, the Lattice IS40 is a small FPGA. So you cannot do all the things which can be done with an FPGA with the IS40. But these are typical applications we are aiming and we are doing hardware for, like logic analyzer, control systems, design education. This is the way for us to go forward. And what is the specific is here the embedded bitstream generation, which can only be done with the open source toolchain. In the field, you collect data, you make a query in your database, and you define, okay, I will generate in the field a new bitstream and program the on-premises FPGA with a new bitstream. I don't know yet where that might be really useful, but it can be done. That's our webpage, icoboard.org. So you find a lot of information there about use cases, about functional blocks which are available, the board you can get there, tools, Yosys the synthesis, simulators. So there is an ecosystem around FPGA, and we try to push the ecosystem. There's also the FOSSI Foundation, which is collecting these functional blocks. RISC-V is an initiative from the University of Berkeley for an open source instruction set for CPUs, because everything is open source except the instruction set. Like there is ARM and there's x86, sorry. And there is no reason why there should not be an instruction set open source, and they defined the instruction set for this CPU, and we implemented this CPU on the FPGA. So what are we looking for? We want to grow the FPGA ecosystem on all corners. IP blocks, Verilog blocks, functional blocks, nice demo cases, learners for innovators, integrate new development tools, whatever. So I hope this will be a bright future. I'm doing open source evangelism since 25 years. 25 years I stood in front of audiences like you here, but I spoke about Linux, and it was like, hey, Linux is an operating system, you can change it for free, and so on, oh, it's stupid and it cannot be reliable, and so on. So, okay, the Linux thing is done, so now attack this one. Thank you very much. What is Lattice saying about reverse engineering their chip? Because this is usually the first question I am asking myself. We wrote an email to them and telling them what we are doing and explaining them, and we didn't hear back from them. So they know and they don't care. Questions? Yes, there's the GCC compiler for the board, yeah. So we also ported Contiki operating system to the RISC-V processor on the FPGA. There's currently a project going on. It's on GitHub. It's work in progress. We will see when it will be done. Sorry, I can't hear you. Can you come front? There is the SPI, there is I2C. We support everything which is on the chip. I think we have a better understanding of the chip than Lattice itself. Because Lattice bought that chip from BlueSpec, and they went off and founded another company, so no one is left in the company who designed that chip. And we found a lot of bugs in the documentation. So we support everything which is in the chip. Yeah. Well, the thing is, I would design it in MATLAB or any other tool to configure it and to design it, and then write the Verilog code and then compile it and do it. So it's like the designing is usually done exterior, and then it's implemented in Verilog and put in the FPGA. So this is also done on the commercial usually. So there are no PDA tools within the commercial tools from Xilinx and Altera. Those are usually external motion control tools, and there is Mathematica and other tools which support the design of these PID loops.
Is there more reliable?
Is it more reliable? No, does it prevent Turing's halting problem? Turing's halting problem. Omega constant.
Yeah, okay.
Cheating constant.
Is it more reliable?
No, you said it's reliable.
Yes.
So does it prevent Turing's halting problem?
Okay, okay.
No, it has not proven Turing's halting problem. But the thing is, the Yosis tool is also a formal verification tool, and you can prove a lot of things with Yosis, but I'm not a formal verification expert. But if you're interested in formal verification, please get in contact with Clifford, because this tool is used also in internal competitions for formal verifications.
Okay. Утре в залата на Олемек ще имаме хакатони. Един от хакатоните ще бъде и за FPGA-ки, като целта ще бъде не да навлизаме в някакви детайли, ами за хора, които въобще не са се занимавали с това нещо и искат да си топнат краката, нали, във водата, да видят какво е FPGA, как се програмира, какво може да се прави с него. Ще имаме такъв воркшоп. Ще използваме същите open source тулове, ще покажем как се инсталират, как се програмира FPGA-ката и как става всичко общо взето. И понеже питахте за PID алгоритъм, принципът е следния. FPGA се ползва само когато трябва, защото обикновено губиш много повече време да направиш нещо с FPGA. И в случая предимството на FPGA-ките е, че те работят с страхотно бърза скорост. Тоест, ако е някакъв бавен процес, искаш да регулираш температура, въобще не ти трябва FPGA. Направи го там на JavaScript, ако трябва. Но ако ти трябва да управляваш някакъв лазер, модулация на лазер, където трябва да работиш в рамките на наносекунди, пикосекунди, там вече няма как да избегнеш FPGA, защото всичко друго е бавно и стигаш до FPGA. FPGA какво е? Все едно, че си чертаеш една електронна схема и след това казваш на компилатора, вкарай ми я в чипа, като тези крачета идват тези сигнали. Оттам нататък ти трябва да си достатъчно кадърен, за да си представиш нещата на хардуерно ниво. Тоест, PID алгоритъм какво ще са някакви регистри, които ще ти пазят стойността, която четеш, стойността, която си задал, пък ще имаш някакъв умножител, който ще ги умножава и ще си направиш формулата за управление. После някакъв ЦАП ще ти конвертира това нещо в управляваща величина и ти си я рисуваш тая схема, даже не е необходимо да я рисуваш, ти само я описваш и казваш, тук имам регистър, тук имам събиране, тук имам умножение и след това нещо това се вкарва в чипа и започва да работи на, да кажем, 500 МГц так. Тоест на всеки там 500 пикосекунди той изчислява всички тези работи и управлява устройството. Това е предимството на FPGA-ката неща. Да, те са външни, да кажем. В една FPGA-ка нямаш цапове ACP. Логиката, която я имаш там.
Well, maybe picoseconds not. But the thing is, the FPGA we have is running at 100 megahertz. So if you divide 1 by 100 million, then you know how precise the timing is. So you never can achieve that. Yeah. Well, for example, you can use a PID control loop when you do power supply control, because then if you really want to regulate with 100 megahertz, with 1 megahertz, then you need a very fast PID controller, but only for really very fast processes. For example, if you want to regulate the power supply of a power transistor in a radar application, there you need it. So it's very, if it has to be very fast, it has to be very precise, it has to be very reliable, then you need an FPGA. I don't know of a commercial implementation of our toolchain. I know of commercial implementation of the processor in real chips. The tools are used for real chips, but the toolchain for the FPGA in a commercial application, I don't know. No. Any question left?
About the size. Is it applicable for Oberon platform? It is RISC-V?
The question is the size suitable for Oberon? Oberon is from Mr. Wirth from Switzerland, a project in the end of the 90s. He did his own processor, his own graphic interface, everything. Actually, I sent 2 weeks ago a board to a guy in Germany who is porting Oberon to our board. So it will be done. So wait and see. Now, well, the thing is, we have two versions. One is with 1 megabyte. The FPGA is large enough for the CPU and for all the controllers, but 128K, as Steve Wozniak and Stephen Jobs found out, is not enough for a frame buffer for the video interface. So we had to use 1 megabyte for the frame buffer, so to work with Oberon for the graphics interface. But it's 50K for the frame buffer. It's black-white, so it's easy doable. So yes, Oberon fits and will be done. And anything which was done before the year 2000, any computer will fit in our board. So it's just like any 16-bit, 32-bit processor fits in the FPGA. So it's used, FPGAs are used a lot for retro computing. Okay. Thank you very much.